Hey guys, Miss Marusik here, and in this video, we're going to look at some additional examples involving electron configurations and orbital diagrams. Now, the first example we're going to look at here is kind of an interesting one. It reviews a few things that we've talked about in the past, and you're also going to see us construct something that might look semi-familiar to you because it's something you probably did back in middle school. We're just going to add something to it. So to start us off here, it says that we're going to be using bromine 71 isotope. So we see that hyphen notation there, and they have told us that this has no charge. So the first question it asks, is this an atom or an ion? And hopefully we see here that this has no charge, so that means we would be dealing with an atom. Next, to figure out my number of protons, I would want to find bromine on my periodic table. I see that bromine is number 35 for the atomic number, and so that means it would have 35 protons to it. Number of neutrons, remember I'm going to use that hyphen notation. The hyphen number tells me how many protons plus neutrons together I have. It tells us the mass number. So what that means is that the neutron count must be 36 because 36 plus 35 would equal 71. Now, to get my number of electrons, this is where I would use the fact that I had no charge, that this was an atom. And so therefore the positive protons and negative electrons are canceling each other out. And so this number 2 should be 35. So next I would fill in my nuclear symbol. As a reminder, I put my bromine symbol in the middle, my mass number on top of 71, my atomic number on this bottom corner, so 35. And since this was an atom with no charge, I can leave that top corner blank. All right, so next I'm going to write my electron configuration. So I would want to think about, where does bromine fall in my filling pattern? And so what I did is I went ahead and jotted down where bromine is on my filling pattern, and we're going to write everything we went through in order to get to that bromine. So that same electron configuration pattern that we've been using over and over again. So starting here with 1s, I go through 2 blocks of that, so 1s2. Next is 2s with a 2 for the 2 blocks I go through. After that is 2p. I go through 6 blocks of that. Next in my pattern is 3s. I go through 2 blocks of that. Next would be 3p. Again, p is 6 blocks long, so I'm going to have 3p6. Next would come 4s2. After that, I would go through 3D. As a reminder, D is 10 across. So I'm going to write down 3D, 10. And then I have 4P, but I have to be careful here because I'm not going to go all the way to the end of the noble gas. I'm going to stop at bromine. So that means I'm just going to write down 4P5. Now, if we did this correctly, remember all of these exponents that we put should total to be the number of electrons, or 35. And in fact, it does here. So the next thing we would want to do is construct our orbital diagram, which of course is the thing with the boxes and the arrows to show those individual orbitals. So first with 1s, for s I always draw only 1 box. I'm going to label that box and I'm going to put my 2 arrows in it. 2s, so again for s I draw 1 box. I'm going to label it, put my 2 arrows. Next would be 2p. Remember, for p, I draw 3 boxes. I'm going to hook those boxes together. And I'm going to fill it with 6 arrows. Now, I am going to follow Hund's rule. I'm going to put 1 in each before I double up. But remember, if they're all full, it doesn't really matter how you fill them up. Where it really makes a difference is on our last sub-level. You got to be really careful on that one, on how you're filling it up. So then again for 3s, for s I only draw 1 box. I'm going to put in 2 arrows, and I'm going to label that 3s here. For 3p, again, I'm going to draw 3 boxes for p. I'm going to fill that up with 6 arrows. And I'm going to label that 3p. For 4s, again, for s, I draw one box. For D, I draw 5 boxes, all hooked together. 1, 2, 3, 4, 5. I'm going to label those 3D, and I'm going to put my 10 arrows inside. Again, I'm going to follow Hund's rule, put one in each before I double up, but since they're all full, it didn't really matter so much. And then finally, for 4P, again for P, I want to draw 3 boxes hooked together. And here's where I have to be really careful how I'm filling these. I only want to show 5 arrows, so I should put one into each before I double up. And so then there's your orbital diagram. So now what we want to do is we want to take this information and kind of blend it with something that you did back in middle school. Back in middle school, you filled out some diagrams that had a whole bunch of rings around it, where you put dots on these rings to represent your electrons. And we're basically going to do the same thing here, except that we're going to also include some labels of what sublevel these particular electrons are located at. That way we can kind of see the blend between what you did in middle school and what we're doing now. So starting here on the first energy level, according to my orbital diagram up here, the first energy level only had 2 electrons. So I'm going to put 2 dots on that energy level. And in middle school, that's all you would do. Here we're going to label these as 1s and 1s. Both of those are 1s electrons. Okay, so now I'm going to go to the second energy level. Well, on the second energy level, I have 2s and 2p, and that's a grand total of 8 electrons. Now, back in middle school, you would just put the 1, 2, 3, 4, 5, 6, 7, 8 dots there. What we're going to do is we're going to go ahead and label those dots with the sublevel they're in. So 2 of those electrons are in 2s. And then the other 6 electrons are in 2p. They would actually be in hourglasses. Now, I'm not showing those hourglasses, but by writing p next to them, that would indicate that they would be in that kind of shape. Okay, so next, I have the third energy level. Now, here's where it gets kind of interesting. I have 3s, 3p, and 3D. Now, I know back in middle school, some of you are like, man, I feel like I only drew 8 dots on that third energy level. You probably did, because I'll be honest, back in middle school, your teachers did not want to have to explain to you how all of this quantum mechanics stuff worked. They did not want to explain to you how in the world to do d orbitals. So more than likely, you only did elements through calcium where you didn't have to include any d orbitals in your configuration. And so you probably did only put 8 dots on that third energy level, but we're going to put a lot more than that here. So we have to have our 2 electrons that are 3s. We have to have our 6 electrons that are 3p. 1, 2, 3, 4, 5, 6. So these are all 3p. And then we also have 3d, and we had 10 electrons there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, these are all 3D. Now, I didn't totally evenly space these. I tried. They're not perfect, but that's okay. We just want to show the correct number on those energy levels. Okay, so next, on the fourth energy level, we have both 4s and 4p. Now for the 4s, there's only 2 of those. So I'm going to have 4s and 4s. And then for 4p, we're going to have 5 of those. So we're going to have 1, 2, 3, 4, 5. And again, these are all going to be 4p. So again, I didn't perfectly space them out along here, but I at least have the electrons on the energy level that they're supposed to go on, which is kind of the important part. So you can see it looks kind of like what you did back in middle school. We're just showing a little bit more information than you did back in middle school. Instead of only putting those dots for electrons, now we're actually labeling what sublevel they go into. And you can very clearly see anything in the first energy level has a 1 in front of it. Anything in the second energy level has a 2. Anything in the third has a 3 in front. And anything in the fourth has a 4 in front of it. So that's how we know what energy level it's supposed to go on. Okay, now they ask us to do some other things for this. The next thing they ask us to do is to circle the highest energy electrons. Well, remember, the highest energy electrons are always the last thing you wrote in your electron configuration or orbital diagram. Well, what was the very last thing we wrote? Well, the last thing we wrote was 4p5. So what that means is that around these 4p's, I would put a circle to show they're the highest energy. And if you want to just remind yourself and write that over here, 4p5, those are the highest energy. Now, the next question asks us to box the valence electrons. Now, here's where this gets a little bit interesting, okay? The valence electrons, remember, are on the highest energy level number. Well, here, anything on the outermost ring that I filled in are technically the valence. They are literally on the outermost energy level. So you can see that includes both the 4p's, so I'm going to put boxes around those, but it also includes the 4s. So those valence electrons are both the 4s2 and the 4p5. Now they ask us over here on this bottom corner, how many valence electrons did we have? Well, count up how many dots you had on that outermost energy level. You had a grand total of 1, 2, 3, 4, 5, 6, 7 drawn. So that means we should have 7 valence electrons, which hopefully should make sense because bromine is in group 17, and we know that that group typically has 7 valence electrons. All right, so now they ask us some additional questions. It says, hey, what is the most likely ion for bromine? And did we lose or gain electrons to form that ion? Well, let's think about bromine's placement on the periodic table. Bromine is a nonmetal. Do nonmetals like to lose or gain electrons? And if you have forgotten, well, think about looking like a noble gas. Remember, if we are having to predict the charge of an element, more than likely it's going to end up looking like a noble gas. Well, is it more convenient for it to go back and look like argon, or to just simply gain one more and go forward and look like krypton? I don't know about y'all, but gaining one more sounds a heck of a lot easier than trying to go back all that way. So I would guess that bromine is likely a -1 for its ion. We gained 1 electron to form that ion. So now it asks what would be the new electron configuration for the bromine ion. Well, let's think about where that 1 electron would go. So looking back up here, think about our electron configuration in those valence. It makes a lot of sense for us to gain 1 more electron into that 4p because it only has 5 right now, and we know it can hold 6. Also, we know if we end with P6, then that would look like a noble gas. It would be isoelectronic, which is the whole goal typically on trying to make an ion when we are having to predict. So I'm going to rewrite my electron configuration. 1s2, 2s2, 2p6, whoops, there we go, 3s2, 3p6, 4s2, 3d10, and instead of 4p5, I'm going to write 4p6. And next ask, would the resulting ion be larger or smaller than the original atom? Well, we've gained an additional electron, so we've gained some repulsions. Remember, negatives don't like to hang out with other negatives. They push out from each other. And so that will cause our resulting ion to be larger than what we started. And finally, it asks, with which noble gas is the bromine ion isoelectronic? Well, we said when we gain that one more electron, we end up having the same exact electron configuration as the next element, which was krypton. So we end up being isoelectronic here with krypton. All right, we're going to go ahead and skip ahead to a few other examples of some various things that we want to make sure we see. So I want us to find where it talks about including the F block. Now we're not going to do both of these. We're going to simply do one of these. And what I want you to see is that by the time we're getting down to where we're including the F block, our electron configuration is going to get really, really long. So it asks here us to do tungsten and platinum. We're going to just do platinum for today. If you want to go back and do tungsten and check it with your teacher, you're more than welcome to. But I want to do the platinum because it's going to help us on our next example. So you can see platinum is way down here at number 78. So we have a long ways to go to get there, and we have to make sure we're showing this for 78 electrons. We got to make sure we're including all of those. Now, I'll be honest with you, we would never ask you to do an orbital diagram that would be this big. Even electron configurations, this one's going to be quite a long electron configuration. So let's think about everything we went through to get to that number 78. Okay, so starting here, we're going to go through 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, then 3d10, then 4p6, then 5s2, 4d10, 5p6, and here's where we got to start to be careful. Next, I would want to go to this 6s, and then 2. But before I get to my platinum that's hanging out over here, notice how this cuts down. Okay, you see it also on your regular periodic table. If you look at your numbers, right now we're at number 56, we're at barium. But before I can get over here, I've got to cut down and do this row that I see down here, or I'm going to be short on my count. So at this point, I have to include my 4F14. So again, I'm going to cut down here. 4F is 14 across, and then I can come back here to 5D. And when I do my 5D, I want to be very careful on the count that I have. To get over to platinum, I have to go through 1, 2, 3, 4, 5, 6, 7, 8 electrons. So platinum's going to end with 5D8. Now, if you did this right, all of these exponents should total the atomic number of platinum. It should total 78. The common mistake I see people make is they leave off their 4F14. And so what happens is if they add up their exponents, they will see that they're 14 electrons short. So if you ever do a double check of your exponents to make sure you have the correct count, if you ever see you're 14 short, ask yourself if maybe did I need to include the F block in my count? Because more than likely that was the situation. Now, obviously, that is a really long electron configuration, right? You're like, good gravy. I feel like that was going on forever. So I have a secret for you. We can actually do a sneaky move and write what is called an abbreviated or noble gas electron configuration. Now, you have to be really careful on a question. If a question clearly says, show the complete electron configuration, you have to write this whole thing. You don't have a choice, okay? But if it says to write an abbreviated one, then you're allowed to use this method, and it will save you some time. How the abbreviated version works is that you would look up the noble gas in the prior period to whatever element you're trying to abbreviate. We would then put brackets around the symbol of that noble gas to indicate that the element has the same electron configuration of that noble gas, plus then we would write whatever follows that point. So for example, you notice the first one on here talks about platinum. So we just did platinum's complete electron configuration. Let's see how we would abbreviate it. So what I would do is I would find my platinum on the periodic table, and I would then find the previous noble gas to it. So you notice working back here, the previous noble gas is xenon. So what I would do is I would start this off by putting xenon into brackets, and then I would write anything I went through after xenon. So if you notice back up here, xenon would have taken us all the way through 5p. So what that means is that this here in brackets basically abbreviates everything to this point. Wow. So now what I went through after xenon is simply the 6s2, 4f14, and 5d8. I only had to include what came after that xenon. So you can see that saved quite a bit of time, right? The reason why these abbreviated electron configurations can be helpful is that I'm still able to pick out the highest energy and the valence electrons. Looking at this one, my highest energy electrons would be the last thing I wrote. Well, the last thing I wrote was 5d8, and so that would be the highest energy electrons. The valence would be in the highest energy level number. So here your valence would be the 6s2, because 6 is bigger than 4 or 5. So I would have 2 valence electrons here. I'm still able to pick out those important pieces of information that I would often be asked. All right, so here's what I want y'all to do. I want you to take a moment and see if you can do that same process for antimony and for mercury. So take a moment, pause the video, and see if you can write an electron abbreviated configuration for antimony and mercury. All right, did you pause the video? Did you try them out? I sure hope you did. So antimony, as a reminder, is Sb. And so what I would do is I would find Sb, which is right here, number 51, and I would go back to the previous noble gas, which happens to be krypton. And so what we would do is we would put krypton into brackets and write everything we went through after krypton, which in this case would have been 5s2, 4d10, 5p3. Now, you are able to double check this with the same method we did before, as far as making sure I showed all the correct number of electrons. I would use the atomic number for krypton, which happens to be 36, and then I can add it to my exponents to make sure that I've shown all the electrons that are in the antimony. All right, now for mercury. Mercury is Hg. Again, you've got to know those elements to be able to find it on your periodic table. So for Hg, I would pick our previous noble gas, which is xenon. So I would come back to xenon, and I'd write everything I went through after xenon. So you should have had 6s2. Hopefully you didn't forget 4f14. And then that went all the way to the end of the 5d block. So you would have had 5d10. And again, if you wanted to double check it, you could ask yourself, well, hey, that atomic number 54 for xenon, if I add that to 2, 14, and 10, would that total the 80 total electrons? And in fact, it does. But again, if you had forgotten the F's, you would have ended up 14 short. And so that would have been a nice double check to make sure that you did it correctly. Okay. All right. With that said, the last section on here that we're going to look at in this video is identifying elements using their electron configurations. So often you are already given an electron configuration and asked to figure out what element that you have. And there's a couple ways to approach that. First off, if you know for a fact that these are what are called ground state electron configurations, meaning that all of the electrons are exactly where they're supposed to be. Nothing's out of order. Then often you can look at the very last element and figure out where in the pattern that fills up at, okay? And match it up then to whatever element that might be. But the other way you can do this is how we've been double checking some of these. You could add up all of your exponents, see what that total is, and see what element has that many electrons. Both methods work. However, I will warn you, in AP chemistry, sometimes we have what are called excited electron configurations, where everything's not in the ground state, in where it's supposed to be. Sometimes things are out of place. And so often the whole idea of counting up the exponents actually works better if you know that some of them are excited. Just looking at the last doesn't always help. So what I want you to do is I want you to take just a moment and see if you can figure out what elements these are. And you don't have to put a name, just you can put a symbol, and that would be good enough. All right, did you try those out? Did you see what you came out to be? All right, so for example, on this element right here, you could either go find where 3p3 ends, which 3p3, 3p starts here at aluminum, and working 3 over would be phosphorus. Or what you could do is add up the exponents. 2 plus 2 is 4, plus another 6 is 10, plus 2 is 12, plus 3 more is 15, and then simply say, hey, what has 15 electrons? Well, the element that has 15 protons is an atom, and so therefore that would be phosphorus. What you should have gotten for these was phosphorus, RH for this element, Bi or bismuth for this one, and then for the last one you should have gotten BH. So you can see if those came out for you. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.